Welcome to The Foundry by Forge College. I'm absolutely thrilled to be your guide today as we explore a really critical topic in our Deploying Smart Contracts with Confidence module, which, as you know, is part of our broader Ethereum Dev Stacks and Frameworks track. Now, if you join us for our last explainer on synchronization mechanisms and patterns, you know we spent a ton of time perfecting how our systems time and coordinate their actions. But, here's the catch. Ensuring our perfectly timed systems are running smoothly doesn't mean much if they are just quickly synchronizing compromised data. Basically, we do not want to automate shipping a dumpster fire at lightning speed. So today, we're making sure our perfectly engineered pipelines are moving the right code at the right time with absolute certainty. Let's get into integrity checks and release verification.
Here's our game plan for today's explainer. We'll start with a welcome to the checkpoint, explore your core verification tools, dive into the three-way verification method, apply all of that to real-world scenarios, build out a pre-automation checklist, and finally, lock down that final gate.
All right, Section 1. Welcome to the checkpoint. Let's take a look at the stakes here.
Before you even think about wiring up release automation into your CI/CD pipeline, you really need to understand what's on the line. If you skip these integrity checks, you might literally just be automating your own disaster. We hear development teams proudly say all the time, "Hey, our build process is totally secure. We have documented steps, controlled inputs, the whole shebang." And that's great. That's a trusted build process. It's kind of like having a beautiful, award-winning recipe. But a trusted binary? Well, that's the actual physical cake sitting at the end of the assembly line. We have to mathematically prove that the cake in our hands hasn't had salt swapped in for sugar along the way. We need verifiable links between the process and the artifact itself.
Moving on to Section 2, your core verification tools. It's time to gather our cryptographic evidence.
To spot an imposter artifact sneaking through our pipeline, we need hard evidence. Enter our very first tool, the checksum, which you'll also hear called a digest. So, a checksum is a deterministic function of an artifact's bytes. You run your compiled file through a cryptographic algorithm like SHA-256, and it spits out a completely unique string of characters. Think of it as a digital fingerprint, but, far less messy than actual ink. If a hacker suddenly tinkers with your code, or even if just a random network hiccup corrupts a single byte, that fingerprint changes entirely. Comparing it against a trusted source instantly rules out basic tampering.
Tool number 2 is the digital signature. A checksum is great because it tells you if the file changed, but it doesn't tell you who actually created it. A digital signature binds that checksum digest to a specific key pair. Think of it as a modern-day tamper-proof wax seal. It explicitly proves exactly who authorized the release because only the true holder of the private key could have possibly generated it. It answers that absolutely crucial question. Did our authorized release manager actually approve this, or was it 3 kids in a trench coat?
And that brings us to our third tool, the holy grail of deployment security, the reproducible-build. This is an environment where the exact same source code and the exact declared build steps will always, 100% of the time, produce an identical byte-for-byte artifact. Reproducible builds are essentially cloning machines. If anyone on your team can run the build locally and get the exact same checksum as the release artifact sitting on the server, well, that provides the strongest possible proof that the binary perfectly matches the publicly reviewed source code. No hidden backdoors, no surprises.
Section 3. The three-way verification. Let's link these together to establish an unbreakable chain of custody.
Now that we have our checksums, our signatures, and our reproducible builds, how do we actually use them together? Well, we link them up. The bouncer at our checkpoint always checks 3 specific things before letting code through. Step 1, verify the artifact checksum. Does the fingerprint match? Step 2, verify the artifact signature. Is the wax seal authentic, and is it from the right public key? And Step 3, verify the signed Git tag. Does this signature point directly back to the exact source code commit that the team reviewed? Source leads to build, build leads to artifact, artifact leads to signature.
Section 4, real-world scenarios. Let's see how this applied verification actually works in practice.
Let's step away from the abstract theory for a second and look at your actual toolkit. Whether you're deploying exact byte-level smart contracts or massive container images, you've got to use the right tools for the job. For checksums on binary releases, you're typically using simple command line tools like SHA-256-sum. For signatures, you rely on GPG or cosign. Reproducible builds absolutely require strictly pinned toolchains.
And for provenance, basically tracking where every little thing came from, you are running SBOM parsers. SBOM, by the way, stands for Software Bill of Materials.
So let's look at a highly practical example, a smart contract release. Imagine your team is ready to push a compiled WebAssembly or .wasm file out to a testnet. Before anything happens, you compare that .wasm SHA-256 digest. You verify the release key signature, you check the annotated git tag. If that compiled .wasm digest is off by even a single character, or the public key check fails, what do? You immediately halt the staging deployment. You literally stop the line right there. There is absolutely zero tolerance for mismatches here.
And hey, what if you're dealing with a container image release? It's the exact same philosophy. You verify the registry digest match, you confirm the build system's attestation signature, and then you deeply review that software bill of materials. Because containers have incredibly complex layers of dependencies, the SBOM acts as your comprehensive ingredient list. It helps us catch any unexpected, malicious dependencies. Because let's be real, absolutely nobody wants to discover a surprise crypto miner secretly baked into their application during the build phase.
Okay, Section 5, the pre-automation checklist. Time to establish our baseline.
Before you hand the keys over to your CI/CD automation and let the robots take the wheel, you must manually run this checklist to establish a firm baseline of trust. Step 1 is preparation. First, prep your environment. Gather the authoritative public keys for your signers. Clone your repository exactly at the release tag. Lock down and pin the exact compiler versions you'll need to do a rebuild. And finally, fetch those SBOMs and attestations. You simply can't verify what you haven't properly prepared to test. Step 2. Execution checks. Now it's time for the math. Compute the artifact digest on your local machine and compare it to the published one. Verify the digital signatures and the key fingerprints to make absolutely sure they match your trusted registry. Cross-check those commit hashes. And if your team has put in the hard work to achieve it, attempt a local reproducible build to confirm your exact output perfectly matches what's sitting up there on the release server.
Step 3. Dating criteria. This is where you draw a hard line in the sand. You must enforce a strict pass-fail policy, require a checksum match and a valid signature, and either a reproducible build match or signed audited build logs. Notice those operators? A failure in literally any of these areas means the artifact does not pass the gate. It's categorically rejected. No exceptions, no, oh, let's just push it this once, allowed.
Finally, Section 6, securing the final gate. We need to create a cryptographic audit trail.
Now you might be wondering, why did we just meticulously do all of that manually if the whole goal is to automate everything? Well, recording these manual validation decisions creates a crucial audit trail that your automation will rely on later. This brings us to a fundamental philosophy in Web3 deployment. Automation requires trust. Trust requires verification. No single verification check is sufficient on its own. A checksum without a signature? Easily spoofed. A signature without provenance? You might just be perfectly signing malicious code. You absolutely must rigorously link every piece of evidence before letting the machines take over.
So I want to leave you with this provocative thought. Will your next automated deployment be a verified success or a totally corrupted headache? The choice is entirely in how you design your pipeline checkpoints today. Thank you so much for joining us at the Checkpoint for this explainer. Be sure to visit forge.college to explore more in-depth Web3 security resources and to get ready for our next topic where we are going to be diving into version control strategies for secure deployments. Until next time, keep your builds reproducible and always verify your signatures.